So we are going to look at the Exam4, and it is related to the nature of light, the chapter 1. Okay, so let's start with the problem 1. A light ray with a wavelength, that is wavelength is given, and enters a block of a plastic from the air at an incident angle of 30.44 37.44 degree. The angle of refraction is this. So the instant angle is known and the angle of refraction is known. Then you need to figure out the Snell's law first. So we need to apply the Snell's law. So n1 sine theta 1 equal to n2 sine theta 2. n1 is the air. Theta 1 is the angle of instance. And the theta 2 is known. And then we need to find out what is n2. And then once we know the n2, then you get these equations. N2 is given by this one. And then the question is, what is the speed of light inside the plastic? So that we need to find out the speed of light in this plastic. And it is given by velocity is c over n. And then if you just plug in the n, then you get this velocity. And what is the index of refraction of a material if the critical angle is given by this number? So n air is this one. So what is have to know is that sine theta c is given by this formula. Note that the refractive index of a medium is here, and note that this index should be larger than the air, which is 1. And then n is given by this formula, and then you can see that n is given by this number. So that it is simple, very simple formula applications once you know the critical angle formula. But what is the important thing is that sine theta is always less than 1, so that you should have a n1 over n2, but if you say that, and then n2, the refractive index in the denominator should be larger than the one in the numerator. Okay. And physics, when a light ray crosses from water into the glass, it emerges at an angle of 30 degrees with respect to normal of the instance. What is the angle of the instance? So now it's time to think about what is happening. It's water and glass. It's not the air and the glass. Okay. So that you have two different medium. One is the water and the other is glass. Unfortunately, the refractive index of water is given and the glass is 1.22. And then we need to find out angle of the instance. So that once again, we are going to apply the Snell's law. And N1 is water, N3 is the glass. Theta 2 is given. The angle of refraction is 30. And then we want to find out what is theta 1. And this is Snell's law, and then just plug in the knowns, and then you need to find out unknowns. Okay. And then you need to change the radians. Okay, so usually some of the mistakes are usually done by changing the degree into radians. So then the pi is 180 degrees, so you need to multiply this factor. And P9, suppose we are using total internal reflection to make an efficient corner reflector. If there is a air n equal to 1 outside and the angle of the instance at the reflector air interface is 50.2 degrees, one must be the minimum index of refraction of material from which the reflector is made. And then in order to have a corner reflector, you note that we need to have total internal reflection. Once again, we require to have incident angle should be larger than the critical angle, and the minimum is such that the incident angle should be same as the critical angle. And in the case of total internal reflection, the formula is sin theta c is n1 over n2. n2 should be larger than n1. Okay, so in this case, n error is 1, and then this is what we want to find out. And then we have this relationship, and then we get this one. So it's a very simple application of the critical angle. Okay. And 13, light traveling in a material level refractive index 1.2 is instant at an angle. Instant angle is known with respect to the normal at the interface with a slab of material that has parallel faces and the refractive index is 1.4. Okay, so that there's two materials. After light passes through this material, it is reflected into the material with a refractive index of 1.85. So it's 1.2, 1.4, 1.85 in the third material. Okay, and then we need to find out find theta 3 in the radian, so that we have to apply Snell's law twice. Interface between the material 1 with the refractive index 1.2 and the 1.4. And then apply the Snell's law once again between the interface between the n equal 1.4 and the n equal 1.85. Okay, so use Snell's law at each interface. So we have this law. Note that theta 2 becomes the incident angle at the second interface. Okay, theta 2 carried out, and then this is going to be what we want to have, theta 3. Okay, so we have a two Snell's law for two interfaces. Okay, and then we want to find out n2 theta 2 is this one, so that this part and this part should be equal. So n1 sine theta 1 is n3 sine theta 3. Surprisingly simple. And then theta 3 is given by this one. And then we get this relationship to find out theta 3. Okay, theta 3 is given by this one. And once again, you need to do the conversion from the degree to the radian. Okay, so it might be a little bit complicated, but it is same as this one. Okay, very similar to the interfaces. And two plane mirrors intersect at right angle. So plane mirror 1, plane mirror 2 is intersect at the right angle, 90 degree. Laser beam strikes the first of them at the point A here. For what angle with respect to the normal of the instance at the first mirror, the angle is from here to here. Okay. And for what angle with respect to the normal instance at the first mirror will this ray strike the midpoint of a second mirror? This midpoint, which is B over 2, okay, after reflecting from the first mirror. So we need to know the law of reflections. Law of reflection is incident angle is same as the reflected angle. Okay. And midpoint of the angle here is that B over 2 is given by this one. And then we need to use this reflection symmetry. And then the reflection at a plane angle, a plane mirror preserves the angle so that you can treat the reflect ray as a straight line from the reflection point to the target point. So from here to here, okay, midpoint. And then what we need to do is that we have to come up with reflection point is here. Let's say this is x, y, so that it is a0, and then it is number is given by this one. Target point is here. This is 0, b over 2. This is x over y. And then we get these numbers. And then finally, what we need to do is that the angle for this angle, yeah, slope of the ray after deflection, the slope of the ray after deflection is a over b over 2. Okay, so it is, so a, and then half point this, it is this angle. Okay, and then this is the theta, and then we can find out from this one, we can get the arctangent, you can get the numbers in the degree, and then you should convert it into the radian. Okay. 3 plane mirrors rather than the 2, then we have a 3. So we 1, 2, 3 mirrors. A beam laser strikes the first of them at an angle of the certain number, 49 degree, and then find the alpha between the ray reflected off and the original ray. This is the alpha. Okay, original ray, and then reflect it back. Okay. So each mirror, we need to apply the law of reflections. The incident angle should be the same as the reflected angle. And then, so 3 perpendicular mirrors, so each reflection reverses one component of the direction of the beta. So here in this case, and then here is the cases, and then if you think about the reflection, so it is the symmetry. It is changing the directions such that if you have an instant, then let's assume that this is the k vector, and then this is the k prime vector, and the relationship between the k and k prime vector is simply because if you just make the decomposition, so this is the downward, but it is upward. Okay, so one of the component is reversed. Okay, this is what it says. Okay, so let's try to find out. So this is what is going to happen, and then so y component reversed, and then in this case x component reversed, and then once again y component is reversed, so that initially you have this component, and then it is minus component. Okay. So angle between the final rays is that angle between the two vectors, initial and the final. The initial and the final, you get the angle between them is given by the cosine alpha is k dot k, k dot minus k, and then you get this one. You'll see that is the pi. So it may be a little bit misleading, but you get alpha is pi radian. And then alpha is actually, we need to find out alpha is given by pi minus 2 theta, pi minus 2 theta. And then you get theta is known, and then alpha is given by this one. Okay. So it is a kind of a geometry problem, but you need to understand what is going to happen. What is going to happen. And then what is happening here is that you can trace back and forth, and then try to identify what it is, what k vector is. And then from the given geometry, you can find out alpha given like this. Okay. The ray of light is traveling in a glass cube that is totally immersed in the water. So that glass and water. Okay, you find that if the ray is incident on the glass-water interface at an angle to the normal larger than 45.5 degree, no light is refracted into the water. What is the refracting index of the glass? So that means there's a total internal reflection. Okay, it's total internal reflection. And the critical angle is this one. And the sine theta c is given by this formula. And then we want to find out what the end glass is. And then you can find out the given refractive index and the given angles. And then you can find out the glass refractive index. Okay. And then light is in some, along the normal here like this, instant ray, the face of AB. And then this is a glass prism of a refractive index of 1.44. And then find the resist value of angle alpha can have without any light diffracted out of the prism. So that what it means is that there should be the total internal reflection. Total internal reflection, and then there is a total internal deflections, etc. So that what is important thing is that you need to understand the total internal deflection first of all. So let's try to read a little bit further. Find the largest value of angle alpha can have without any light refracted out of face AC. Okay, so that we have a water outside and the glass here. Then what is required is that it's normal, so that it should be travel these directions and then refracted back. And then we need to have a total internal reflection at a given condition alpha. Okay, so that is a previous case, we have a instant ray direction is changing, but in this case, the interface angle is changing by alpha. So that's the main difference. Otherwise, it is the same. So here is the case, and then reflected here. So ray inside the prism, light enters the face AB normally, so that no refraction occurs at the entry. The ray travels horizontally here inside the prism. And then geometry at the face of AC. Face AC is inclined to the angle alpha, so that internal angle of instance at the AC here. So if you think about what's the angle of instance for this light, for this interface, and then theta I is nothing but 90 degree minus alpha. Okay, so we can figure it out easily. And then condition for the null refraction is nothing but the total internal reflection. So that limit is this one, theta c is this one. Okay. And then we get the critical angle, and then you have this relationship, and then alpha is nothing but 90 degree minus critical angle, and that's the angle. Okay, so once again, we are applying the total internal reflections. And then in this case, we need to figure out what is the instant angle for the given prism angle of alpha. Okay, the instant angle is this one. Okay. And then instant angle should satisfy the total internal deflection. And then we can find out theta c, critical angle should be same as theta I, and then you get alpha. So we have another one is a polarized. This is the polarization, so that we have an unpolarized light incoming, and then there is a polarizer 60 degree, and then there goes, and then after that 90 degrees. Okay. So usually, if you have just two polarizer which has a 90 degree, then you will not get any light coming out. But in this case, if there is in between, there's another polarizer with the angle of 60 degree, you need to find out what's coming out, okay? So a beam of unpolarized light of intensity passed through the series of ideal polarizing filter with their polarization direction tuned to various angle as shown here. So it's initially this one, and then this angle at that 90 degrees, okay? So for first polarizer will have unpolarized light to the polarized light to these directions, okay? And then for intensity is reduced by half, okay? You have two choices, vertical or horizontal, and then you choose one of them, and then you get this relationship. So after passing the first polarizer, point A will give you half of the initial intensity, and second polarizer will give another reduction, which is given by this Malus's law, this one. So if the angle is making 60 degree, then you get this one, okay? And then if you have a cosine squared, then you get I2. And then it's time to think about this final one. You note that the angle, if you think about this angle is the initial polarization reference to the electric field to the polarizers, so that you need to make sure that the angle between these two polarizer is actually 30 degree. So if you do not calculate right angles, then you will get the wrong answer. So I3 is given by I2 times cosine square 30 degree. Okay, and then if you do the calculation one by one, then you will end up at this one. So first thing is that if you select one of the polarization, then intensity will be halved. That's the first thing. And then next thing is you follow the Malus law, cosine squared theta. Note that angle is between the two polarization axes, okay? And then you get the 60 degree here. And then for the third one, you get the angle between two polarization axes is 30 degree, okay? And then you get this number. Okay, so this chapter is relatively simple. You need to know the critical angle and the Malus's law, and of course Snell's law.